Okay, we're going to get started here. My name's Ken Corum. I'm the other half, Jim's brother, younger brother, not his son, as some of you have come up to us and said. There's only 11 years between us, but I do the experimental part. He's in the library doing the research and comes up with all these wild ideas, and he'll say, well, we need to move this one turn here another 3 inches, and I'll say, forget it, that's going to take me a month. And he says, well, it's easy on paper, you just draw a line here, and away you go. But we get into a lot of arguments as to how to do things and get things done right, and I think we complement each other very well. Just real quick before we get started here on this next piece, I just want to remind you at 2 o'clock this afternoon in the poster room, we will be talking about Tesla's receivers in listening to planetary signals, and we have published a paper. We call it a paper. It's actually book size. It's available over here in the bookstore. It's only $11.50, and it does cover a considerable amount on Tesla's receiver and how to construct them, as well as how they work, and also a lot of information about the emissions of signals from Jupiter and how Tesla could actually listen to those signals coming from Jupiter. And you ought to pick it up. We only printed 100 copies, and once they're gone, that's it. There will be no more printed after that. So grab them now while you can. And again, the price that we charge is just for the charge of the printing. There's no money in it for us at all. So at this point, if we could go to the overhead. We want to start here with talking about the Wardenclyffe Island apparatus. And how did Tesla actually measure the diameter of the Earth within 50 feet or even within 10 feet using this apparatus? How could he do it? And that's what we want to focus in on right now. And at this point, I'm going to turn it back over to Jim. He's going to talk a little bit. I'll be back in just a moment, and we'll talk some more about the actual hardware and the construction that Tesla did to measure the diameter of the Earth. Jim? Don't go anywhere. Put it over there. Okay. This is actually just a continuation of where we stopped a moment ago, so we'll just pick right up.
Yeah, let's see. I hope you can hear me. It is on.
Got the wireless? We have the wireless mic on?
It says it is on.
Okay.
Hello, CQDX. All right. I'm amazed at how many ham radio operators are involved with this stuff. I've got to tell you that that's sort of how we got interested in this. In fact, Tesla stuff led to ham radio for us back in, it's 40 years ago. This is 40th year ham radio. I'd say ham radio has changed a lot, but if you're like me, you hang on to all your old equipment. I've got this attics full of HRO 60s and SX99s and Emerald stuff and all those good old things. I wouldn't part with them for Kenwoods and Yaesus and what have you. We want to talk about Wardenclyffe today and operating strategy. What we're after this hour. I want you all to leave at least understanding what our assertions are. We're going to assert that Tesla meant certain things when he said them, all right? Now, maybe we're wrong. We've been wrong before. It's not a sin to be wrong. Maybe it is, but it's okay. But I don't think so. I think it's like the ball lightning and the helical resonator stuff. It's been there all along. Tesla told us in plain, clear words how to do it. He showed us in pictures, and it's us, and I'm saying us collectively, that have been the boobies. Nothing wrong with Tesla. Right? So those two items are really what we're after covering today, this hour. Tesla and the diameter of the Earth. Look, he made these comments, these quotes. And again, you know, these are troubling. They should be troubling to you if you're a skeptic. about Tesla. How can he say these things? And of course, no one can read this fine print. Up to this day, I'll read it. Yeah, maybe Ken can figure out how to focus it. Up to this day, we do not know the diameter of the globe within 1,000 feet. He's saying this in 1907. My wireless plant will enable me to determine it within 50 feet or less, when it will be possible to rectify many geodetic data and make calculations as those referred to with greater accuracy. I mean, look, we're talking about the one of the first levels for the GPS system was around 50 feet. Now, of course, let's see. I could calculate exactly, in 1922 he says, I could calculate exactly the size of the Earth with the size of the Earth or the diameter of the Earth and measure it exactly within 4 feet with that Wardenclyffe machine. Now, of course, he's not talking about, we know the Earth's bulgy and all that stuff, but he means the mean diameter, of course. Okay. Let's talk about the Long Island apparatus. Kenny's got... We both went there back in, was it 83, 84, somewhere in there. Peerless Photo owned it. I guess they still do. Or AGFA owned it. Yeah. And they were very helpful to us. And they wouldn't let us in the building because of the chemical processes that they were. But they let us walk around where the tower was and so forth and see the facility. And we'll show you some of the slides from back then. And you'll notice that we look a whole lot, well, we've changed since then. Huh? Frequencies used, 1,000 hertz, 1 kilohertz, he said. Mostly below 30,000, this is Tesla speaking, mostly below 30,000 cycles. All right. Construction work started in 1901, stopped in 1903. The building operated up till 1907. And these are the physical parameters of it. I mean, some of these things will begin to come out in some of the photographs. Ken, you want to talk about? Here's your...
Okay, what we're going to do is take a quick slide tour here through what it looks like today and then take a look at what it was then. So if we can get the first slide here. This is the corner of Tesla and Route 25A. There's actually a street, a side street there called Tesla Street, and Tesla Street actually runs where the spur off the main railroad track runs to dump the coal for Tesla's steam-powered generators. Oh, we got it backwards. It's Route 25A and Tesla Street. What you're looking at here, it looks like just a bunch of bushes. This is actually the base of the Wardenclyffe Tower. It's still there. It's a bunch of granite blocks about 50 feet in diameter with large steel bolts still protruding up out of the granite blocks, the foundation. And they planted bushes all the way around the granite block, so it looks like a circle there. Again, this is Tesla Street off on the side, and you can see the Wardenclyffe building there behind. Here are the bushes around the base of the Wardenclyffe Tower. Again, behind the bushes are granite blocks, huge granite blocks. They probably run about 16 feet long, about 4 feet wide, about 2 feet thick, with huge, probably 1-inch diameter bolts that stick up out of them. Here's a plaque that's been placed on the side of the building. This is looking just about standing, the camera was just about standing in the center of the tower, looking straight back at the building. Again, here's the picture, and you probably recognize the windows if you've ever seen some of the Wardenclyffe pictures. Again, the plaque commemorating Tesla. And this is of interest. It's the cupola. It's the chimney where the steam would come out from the steam-driven generators. This is kind of a fuzzy photograph. It's actually inside his machine shop, and the machine shop faced the side of the railroad tracks, which would be the north side of the building, the opposite side from the tower.
Oh,
here we have the tower.
Bring it down so you can see the top.
Oops. That's all we got. We'll come back to that on the slide. Again, another close-up of the tower, wood construction, metal plates, bolts, and so forth. And again, when the tower was finally destroyed, it did come down. But what is of interest to us is up at the top, notice that ring around the top. That was actually a helix. There was actually a lot of wire wound in a very large helix that was stuck up there. In a moment, we'll talk about what that helix did for us. Again, here's the base. There's the bushes around the base of where the tower is today, or would be today. And then clearly we have an image of what Tesla thought might be happening or taking place in the future. And again, oh, how'd this get in there? This is some fireballs that we had done on ball lightning research 6 years ago. And also some particle beam weapon stuff that we had done. That's a directed discharge of about 40 feet or so.
It's 29 feet.
29 feet. Yeah. Okay. Very quickly. If we could go back to the overhead. What we want to point out here is the helix around the top of the tower. It was a very large coil, not quite sure of its material that it was constructed out of, but it does make the case for measuring the diameter of the Earth, as we'll see in just a moment. Inside, very quickly, here's the machine shop. This would be the side that faced the railroad tracks, the north side of the building, opposite the tower. Okay, here's his laboratory, the electronic shop. This is the part that did face the tower, one large room. Now, when I was over there in the museum in Belgrade in '93 of September, there were a number of other photographs that haven't been published yet, which show the insides of this in a little bit more detail in some of the other rooms. Actually, there was one large room in the front, one large room in the back, a balcony over the machine shop area, and a generator in the center of the building, a coal room off on the east side of the building, and on the west side of the building there was a generator room. This was a 200 kilowatt two-phase generator which he had on the west side of the building, and it operated at frequencies from very low frequencies like 100 hertz or so all the way up to 7,000 hertz. So this was actually an alternator apparatus. Now, what was he doing with 7,000 hertz or alternations up to that frequency when clearly the coils operated at much higher frequencies? Again, this is the inside of his laboratory. Notice his flat spiral coil, which he did use, and power transformer in the front there, and a few other pieces of apparatus. At this point, turn it back over to Jim, and he's now going to take all this information that we've just seen in the pictures and now put it together and show how you could actually measure the diameter of the Earth using this equipment. Jim?
Well, we're going to try to. That's yours, I guess. Okay. Tesla published an article in May 1919. That's it. Okay. Issue of Wireless Experimenter. Again, realize the audience that he's got, he's really talking to experimenters, and so he's going to try to tell it to them in language they can understand. But we're going to try to take it literally and see what problems we run into. This sketch corresponds to Tesla's, which appeared in the May 1919 issue of Electrical Experimenter. It illustrates the effect of a large capacity on one end of a single wire transmission line. Let's see, he has similar drawings for the voltage distribution in the Colorado Springs notes on pages 103 and 197. But let's see, in 20 words or less, the idea that he talks about is that, all right, if I take a single conductor that's of length, let's say, or height h. Let's do it as a balanced dipole here, say first. Length h, and I excite this thing at a resonant frequency. The spatial distribution of the voltage is going to be something like this, and the two ends will be 180 out of phase. There'll be a node in the middle, but I've got a small capacity at both ends, all right? And then Tesla proceeds, and he says, well, look, suppose I make one of the capacitors real large at one end. What happens to the node? And of course, what happens is the node physically moves. And of course, you can see where we're going to go on the Long Island, on the Wardenclyffe Tower. We're going to look for nodes going up and down. You know, his tower was, what, went down about 120 feet into the ground and came up about 157 feet to the bottom of the platform at the top. So, and we've got that distance, and then the ball itself, I think, is a diameter about, what, 50 feet or something like that. Okay. So you'd say, well, all right, I could measure, since I know if I assume the Earth is a perfectly conducting sphere, you know, and I know that theoretically the capacitance of a sphere, if I don't have to worry about where the electrode connects into it, I take good care of that like you would with a Van de Graaff or something, right here and up above. If I can get my electricity to be more or less uniformly distributed over the whole structure, then I know that the capacitance of this is 4 pi epsilon sub 0 times the radius of the sphere, see? So all I have to do is, with this thing, is set it up, tune the thing to resonance, measure the resonant frequency, and if I know the capacitance of my ball up on top of Wardenclyffe, and I know the spacing here, then by measuring how far this node moves, I ought to be able to determine the radius of this, the capacitance, and therefore the radius of this sphere. All right, it's a nice argument, but if you put some numbers in it, and again, you got to realize the audience, this is not a letter, or not an article that's written in Physical Review or published in the Proceedings of the IRE, so you got to realize the audience he's talking to, and I think he's talking in general concepts here. If you do this lump circuit, this LC equivalent circuit calculation, the focal plane on this thing must be about paper thin, because when it curves up just a little, I notice the focus is really poor, but most of you are asleep anyway, so that's all right. Let's see, the capacitance of the tower. And again, these are just for rough calculation purposes. I mean, the tower is, the radius is 33.75 feet, an effective radius anyway. The distributed inductance of the vertical shaft, we can do that calculation, is about 1,140 picofarads roughly up on the ball. So many microhenries per meter along the shaft. We'll assume a number for the radius of the Earth. We'll just take a number out of the CRC handbook or something. And get the isolated static capacity of the Earth, and then go through Tesla's calculation to find out where that node is. And lo and behold, the node is about 0.161 millimeters up from the base of the shaft. Right? Well, there's no way you're going to measure on a 120 plus 150, what's that, 270 foot length of pipe. You're going to measure a node moving 1/10 of a millimeter. You're not going to see it, right? Obviously. So, well, conclusion, you can't measure the capacitance of the Earth this way, with any precision anyway. But Tesla said the same thing. He said, look, when the capacity C becomes commensurate with that of the Earth, X, that's the distance down to the node, approximates L, the spacing there. And in other words, the node is close to the ground connection, and he's telling them that. So we think that this is sort of an explanation for youngsters, to give them an idea of what's going on. But we said, look, and by the way, the mathematics behind this, again, is in the paper. It'll be published in the transactions or the proceedings when they publish it. So once again, we're making assertions at this point. And you don't have to believe the assertions we make. To recognize that when somebody makes assertions, they've made certain presuppositions, and then you want to follow the logical progression. You can come to a logically correct solution, conclusion, but your premise or presupposition can be wrong. So, but we're going to make some assertions, and you just follow us at this point. Assertion that we make is that, all right, if instead of using the lumped circuit analysis that we just went through, suppose we do the same argument, but we're going to use a transmission line model. And last hour we went through and we found the L and the C for this equivalent spherical transmission line. And therefore I know it's Z naught. I've got that up there. I also know the velocity factor for it. And I'm going to consider this ball as a piece of transmission line that has a certain length. And I'm going to have a short circuit connection at this end. I'm going to have a direct electrical connection with 1 ohm resistor, in essence, in series there, my ground, and an open circuit on this side. So I've got a piece of transmission line here. And you can treat a ball, spherical transmission line, the same as a linear transmission line if you want, but you got to realize that the capacitance per unit length and the inductance per unit length are functions of the angular distance. So it's henries per radian and so forth. All right, the vertical mast I can treat as a single wire transmission line. It has its own characteristic impedance. We can calculate that. It has a certain length. We go down 120 feet and we come up 150 feet. We've got a capacitor up here. And at the base of the tower, I mean the base of the ball at the top, I'm permitted to put all kinds of linear circuit elements. So I can put a fairly hefty inductor up there if I want, to help tune that C to a resonant frequency, to bring this thing into resonance down, say, in the kilohertz range. We assume the Earth is a single-wire spherical transmission line with the antipode as an open circuit. And in fact, Tesla made the comment in the Colorado Springs notes here on July 24th. He says, the Earth behaves simply as an ordinary conductor, like a wire. And it will be possible with a powerful apparatus to produce stationary waves, which I've already observed in the displays of lightning and so forth. Now, we'll want to come back to this, but we want to do some calculations now on this model and see where the nodes, the standing wave nodes, move on this thing. All right, well, again, you'll just have to take our word for it that the series impedance, let's try and do these two things at once. The series impedance connected to the top of the pipes, that's up at this end. So I'm going to be looking from the top of the pipes into the ball and whatever big inductors I happen to use up there with it, connected in series. I'll have a series impedance, it's a lump circuit up there, so I can use ordinary lump circuit analysis, J omega L1 plus my top capacitance. And that gives me the impedance looking this way. The open circuit loaded single wire spherical Earth transmission line, impedance looking in here at this end. You know, from where do we cover this? Usually in the second course as an undergraduate EE, you cover transmission line, ordinary transmission line. I've got an open circuit on the end. I can bring it forward however long this is in terms of wavelengths. And that gives me my impedance seen looking this way. I know the characteristic impedance for my spherical transmission line. I also know its velocity factor. And we include losses. So we'll use a hyperbolic cotangent here. And finally, I get the input impedance seen looking down from the junction at the top. So I'll take this impedance right where I make that connection and transfer it up to here. And then connect these two. And then what I'm going to do is tune until those two impedances are conjugates of one another, and I've got the resonant situation. Okay? The input impedance seen looking down from the top of the tower matches all this up. So now we've got a nice transcendental equation we can solve. But we know all the parameters that go in there. And we can predict the VSWR pattern now on the tower. Here's the voltage distribution on the tower, as it would be on any transmission line. And now what we have is a distributed analytical model corresponding to Tesla's lumped element 1919 model that he gave to the youngsters that read Gernsback magazine. All right, let's put some numbers in, just to see if it comes out any better than 1/10 of a millimeter. See, numbers we use. Well, we put up on the top about a 20 Henry choke. That's a big amount of inductance up there, but our frequency is going to be down around 1 kilohertz. I think we used 1,030, it says here. Right? Why 1,030? Well, it's 1,000 because he said he was operating down at 1,000. We haven't told you how he got it yet into the tower. We'll have to do that. 1,100 picofarads in the top. Characteristic impedance of the vertical pipes is about 125 ohms. 60 ohms was the characteristic impedance of the spherical transmission line. That's the square root of L over C. We took the phase velocity just to be the speed of light on this one. Now, when you plot the voltage distribution, you get a whole family of curves depending upon what the radius of the Earth is. Think of the Earth now. Those of you that are microwave engineers know about trombone matching networks. Now, think of the Earth as a trombone. And if I move it in or move it back, I'm going to move my VSWR pattern around a little bit here. But the problem is I want to know what the length of my trombone is. All right? That's what we want to solve for in this thing. It's a kind of a peculiar problem. But as you change the, we pick a frequency, and as you change the diameter of the Earth, so we tune the Earth, make it a bigger Earth or a smaller Earth. The VSWR patterns actually go like this, okay? The magnitude of the voltage. But so what we're doing is we've zeroed in on the notch apart. This is volts along here versus position along the pipes. Okay, so I mean, I'm going to start with 0 at the bottom. When I get to the level of the Earth, that's here at ground level, that's about, it's about like, what, 38 meters. It's 120 feet, whatever that is in meters. And then as I move up to the top of the tower, I move all the way up to here, where it says top, of course. So the issue is then that with a distributed model, if you were observing the VSWR pattern at these real low frequencies, it looks like you could indeed see a notch. Now, how would you detect the notch? No problem. If you ask that question, you probably don't belong in this room. If you've got an NE2 in your pocket, you run up and down the antenna, all right? And where the NE2 goes out, I mean, that's where you've got the voltage minimum. I see some hands back there shaking their head. Yes, they've done it many times. I can recall as a kid, I didn't have an NE2, but I did have an old fluorescent bulb. And put it on a bamboo pole and ran back and forth across the yard trying to find out, you know, if I was tuned or not. What you're looking for is to see if you've got your feeders at the place where you happen, you know, if you're trying to do the thing feed it at a current point, you want to see if you've got the feeders at the place where the bulb will go out. Well, it's the same sort of thing here. And of course, by the way, we mentioned NE2s. Tesla invented those in the early 1890s. He didn't call them NE2s, of course. All right. So the bottom line on this is that, yes, the distributed model gives you numbers that are real. You can use real-world numbers, and it gives you stuff that is consistent with what he says. Let's see. You need to know this. The procedure is you calculate and plot the voltage distribution along the vertical pipes for earth radii stepping in increments of 5 meters. That's what those steps are. The figure is a blow-up of the notch region of the VSWR pattern. That is, it's the magnitude of the voltage as a function of the height along the tower. And you explore the voltage minima. And the question, well, what kind of delta Y by delta R equivalent for the Earth do we get as we move this thing? So if I move so many meters on here, what's the equivalent change for the radius of the Earth? And what we got is about 1.75 feet. Now, to be sure, this is on paper. All right? Now, Tesla said, what, 40 feet? I think I read it to you a few minutes ago, maybe even as low as 4 feet. It seems like you know, a reasonably prudent person would grant him a little bit of latitude here. I think that there's something to be said for what he was telling us about. Now, that ball gave us the idea of something else that's going on here. I think you'll find this interesting. Oh, look, there's a lot of arithmetic on there. Don't worry about it. It takes arithmetic a lot of expressions to say some things that are fairly simple, and I'll try to say it both ways, because I know I've got two kinds of people here in my audience. Many of you are familiar with Fabry-Perot interferometers, you know, where you have two conducting planes, two mirrors like on the end of a laser, only we're not using a laser here, we're using a linear medium in between. You can do it the other way around. Instead of having the two mirrors on the end and insulator in between, you can have conductor in the middle with insulators on both ends where your mirrors would have been. And the thought occurred to us, well, look, if we modeled the Earth, that transmission line that we just had, as the dual to a Fabry-Perot interferometer, the voltage distribution along the interferometer would be the same as what we would expect over the surface of the Earth. Or at least along the projection on the diameter of the Earth. 5 minutes. Yep. Ah. Oh, man. Well, there's a lot of arithmetic here. If we have these, the analysis is fairly simple. We have traveling waves, and they propagate and reflect off the mirror, and they go back and forth. We're going to do it with not just a single carrier wave, monochromatic wave. We're going to do it with a carrier whose sidebands we can move in and out. This is exactly the same experiment that we did and told you about, we did back in '93 when we measured the transverse resonances of the Earth. This at the top is the envelope. And for this, I forget what frequency we're using here. Let me read it. This sketch traces the propagation of one of the two sideband traveling waves on the resonator. The total voltage on the resonator is found by summing the two separate traveling waves for both the upper sideband and the lower sideband, and then adding the two, superposing them together. So that would give me the total phasor interference pattern. The result is the upper sketch, okay, which oscillates at the carrier frequency. As you change the modulation, the spacing between the two, the envelope of that beat pattern, the envelope changes. All right? A modulation resonance occurs or is observed whenever the envelope has a period commensurate with 2 times the distance between the two divided by c. All right? So you can have a period for the modulation that has a half wavelength that corresponds to the distance between the two reflecting objects. You'll get this sort of interference pattern. But no interference, those of you who know something about optics, no interference occurs unless these traveling waves are coherent, all right? Or at least are coherent over a long enough time to be able to interfere. All right? So you may have some fairly broadband signal. Oh, don't let that guy in here. Oh, no. You're not supposed to come for another 15 minutes. He's laughing. The signal's coherence length must be 2D for interference to occur. What do you suppose that when you do the calculation for the Earth, you get that coherence time is 0.08484. All right, just as Tesla said. Look, those of you that are familiar with optics know about the finesse of a resonator. And the finesse of a resonator has to do with the, it's similar to the cube, but it has to do with the sharpness of the, it's actually the separation between, every time you get to another resonance frequency, and to the radius of the structure here. What we did was we did the calculation now when we changed the carrier, we did the interference pattern calculation for waves over the surface of the Earth using Zenneck wave attenuation. And we did it for carrier frequencies at 6 kilohertz, 12 kilohertz, 18 kilohertz, 24 kilohertz. And what you find, of course, is that, and of course, we've normalized everything with respect to 6 kilohertz in this drawing. You see that the resonances begin to wash out when you get up above 24 kilohertz. Just as Tesla said. He said, you don't want to go, he says 30 kilohertz, forget it. And on this, the future of wireless transmission of power depends. If you take the numbers that test, these, how can I say this? If I vary the modulation frequency, one of the things that astonished us was that if I put a transmitter on one side of the Earth, and sweep this modulation frequency, thank you. The projected distribution, voltage, that beat frequency pattern, it's not a beat frequency pattern, it's a standing wave pattern projected onto the diameter of the Earth looks like this. R is a receiver and T is a transmitter. All right. Now, I was doing this about a year ago in April, and I about dropped my teeth when I saw this because I wasn't expecting this to come. Because this drawing, lower drawing, is one that Dr. Mrencich published a good many years ago. Dr. Mrencich published this in 1982 in the IEEE Transactions on Power Apparatus. This page is from June 2nd, 1901, from Tesla's notes. And sure enough, he's drawn this exactly the same thing. So he's using the same ratios that I'm using in the theoretical calculation. The only difference is that we're separated here by more than 90 years. And of course, mine is done on a computer, and his is done the only way he could have done it, and that's by experiment. By the way, the resonant frequencies on that optics thing that we just gave you were, the frequencies of resonance occur at 11 point, let me give you it to 3 decimal point places, 11.778 hertz. Now, I know you can't measure that close. Maybe you can, but what's important there is that, lo and behold, that's not the 7.5 hertz that you get if you were exciting Schumann resonances, number one. And number two, Tesla said in September 24th, 1921, a skillful experimenter who is in the position to extend considerable money and time will undoubtedly detect waves at, and he gives the wavelength, and it corresponds to 11.779 hertz. I mean, we're off by 1/1000th of a hertz different from what's predicted. Only he published that in 1921. He didn't have the calculation. All right, something else. 2 symposia back, yeah, you know, it was about, what was it, 1992. And the transactions, the proceedings are over in the library, the bookstore, and you can buy them. Doctors Spaniel and Sutton gave a, you know, their measurements. They were looking for Schumann resonances, and they were kind of disappointed. In fact, they called me up one day at Battelle, and they said, you know, we're not seeing this stuff at 7.5 hertz. We're seeing this stuff up at 11.8 hertz, and it's got Qs in excess of 1,000. They said, that doesn't make any sense whatsoever. And I said, oh, it must be spurious data. You know, it's an artifact. You know, the sort of things that you say when you don't know what you're talking about. And somebody ought to nominate those guys for Nobel Prize, because they measured with the same Qs at the same frequencies that Tesla is telling us about 90 years ago. Okay? All right, well, let's see. How are we going to do this? How much time is left, Kenny?
This is it.
Now, if you run real fast, time slows down. This section was, we said all of that to tell you this. This is the operating strategy. How could you make such a transmitter work down there? Can I have
Nope.
1 minute, 2 minutes?
Really tight this morning.
Yeah!
But you do have another shot.
I don't.
Remember, at 2 o'clock.
Let me tell you. Look. One slide. We'll say it in one slide without telling you why. Just we're going to make another wild assertion. This is from 645576, famous patent, all right? And Tesla draws this. Notice he's got a generator here, ground connection. This is a resonator. This part's a resonator. He's got one over there. The assertion that we're making is Tesla is, that's a real honest-to-goodness alternator there. It's running at 1 kilohertz. And you and I both know that we're not going to get any 1 kilohertz, and you might get voltage induced in the secondary, but there'll be no current. Ha ha ha. When you read what Tesla says in Lee Anderson's book, he says, oh, I use both high frequency and low frequency. Boing. Connect around this, the RF port. We all build Tesla coils, not like this. We all build them with the other part stuck on over here, see? Once you've got your RF going, and you've got some plasma at the top, and you've got some free electrons, everybody knows that if you get corona on the top, the corona capacitance might give you 10%, all right, at RF. When you pump that RF plasma, the Debye shielding is a whole lot less for these 1 kilohertz waves. And what happens is the induced voltage superposed over the top of the RF, it's not modulation, it's superposition. I've got RF about 100 kilohertz to make some corona, but I'm pumping the electrons in that corona now, and now I'm able to get ground currents to flow down at 1 kilohertz, 5 kilohertz, all right? And with very little attenuation. We think that this is the technique for launching Zenneck waves, and I gotta stop. That's all I have to say.
Thank you very much. And remember, at 2 o'clock, we can get deeper into this in the poster room with the Corum brothers. And oh, boy, I wish I could be there. And I think they're going to tape that session, too, if I'm not mistaken. So that should help as well, because I know we're going to have a very, very crowded afternoon today, as we have a fairly crowded morning. So we have about a 5-minute break after I tell you a couple things that have been figured out. First of all,